All right, folks in the back, good? I need a thumbs up from someone way back where. Yay, great. People are hearing me already. All right, good afternoon, everyone. Welcome to this session about optimizing your serverless applications. The goal here is to earn your black belt, which means it's an advanced session, 400. I'm going to spare you the basics of what is serverless and serverless architectures and just get right at where you'll be tightening your screws to get the most out of it. I'm Ajay. I lead the product team for AWS Lambda, and I'll be joined later in the talk by Peter Spassky, VP on A Cloud Guru, one of our favorite serverless startups. Woohoo! Yes. You're all here because you're one of the hundreds of thousands of developers across a huge range of companies who have chosen to go into production with serverless applications. You're in good company from successful companies like Adroll, Airbnb, Nextdoor, IoT leaders like iRobot, Fortune 500 companies like Coca-Cola. Companies of all sizes and shapes have moved to production with their applications. What's been really exciting in the last year for me personally is seeing these customers start to push the number so much higher when it comes to both scale and performance. And you'll hear many of their stories at this talk. Hopefully many of you have those stories to share with those around you. Please wait till I'm finished talking. For example, Fannie Mae is doing about 20,000 concurrent requests on Lambda, which translates to them processing loan simulations for over 20 million loans in just under 2 hours. Nextdoor has built a serverless data processing system which processes about 5 billion requests a day. Vogue has improved the performance for their image processing and image rendering on their website using Lambda and API Gateway by almost 90%. Now, all of these customers, and many of you included, have made this move to improve a few things. And it boils down to elasticity, resilience, and agility of your application development, all with a background of cost savings. Obviously, going serverless and offloading responsibility of utilization management and server configuration can have a major difference to how you build, own, and operate. And it also means that getting these gains on performance and cost optimization comes with a spectrum. We believe that there are a core set of practices that every developer needs to start following to get the most of your serverless architecture. The typical layers of a serverless architectures, and there are a few. And before I actually get into this, one point to mention is when we talk about optimizations with conventional architectures, we talk about packing more onto individual boxes or fine-tuning your CPUs or tweaking that network switch. That is not a layer that you have to worry about. That is something I sit and sweat about every single day. What your problem becomes is what you do with your application code, and that's what we're going to talk about here. So, a typical serverless application has a few layers. You have your access and authentication layer across a multiple set of services that's responsible for deciding the ingress, authentication, access to your backend layers. You optionally have a messaging and orchestrating tier that is responsible for coordinating calls to your backend, doing some kind of buffering, state management, collation of records, batching, etc. Obviously, the compute layer, my favorite, where all your business logic actually goes and executes. And then finally, the data layer, which is responsible for state, durable information that your application needs, or sometimes even third-party applications that you access through APIs, potentially running on your own systems. The same layers apply whether you're building end-user-facing applications, which has a certain flow, or back-end applications, where maybe only a couple of these layers are actually in play. Now, this is obviously a huge surface area for me to talk about, so we're just going to focus on one specific area of optimization, particularly looking at your functions, the invocations of those functions, and the interactions these functions have with downstream services. Peter is actually going to take all my practices in theory and tell them how they actually put it into play with A Cloud Guru. We've tried to distill all of these practices into 4 katas. These are inspired by the pragmatic programmer construct. We call them the lean function, eventful invocations, coordinated calls, and serviceful operations. Hopefully it all sounds very mysterious and you'll be willing to stay more to hear about it. Now, there's a lot of collective wisdom reflected in this talk. I can't claim to have generated everything that's in here, but special calls out to Alex Casaboni from Cloud Academy, Yan Kui from Burning Monk, and Clay Smith from New Relic for generating some of the tools and analyses that you actually see in this talk. All right, so by the end of this, you're going to walk away with a repeatable regimen for building high resilient, high performance serverless applications. Everything we talk about today hopefully accrues towards three things: reducing the end-to-end latency of your application, reducing the cost of your application, or improving the resiliency of your application. All right, let's get started. So first up, the lean function. The reason I'm choosing to start from the function itself is because that ends up being the most critical component of your architecture. It functions as the glue for all the different components to talk to each other. It controls the business logic, which is ultimately what you're trying to differentiate, and it has significant implications on how the overall application behaves. Now, in order to understand how to optimize the function, you probably need a better understanding of what actually happens underneath the covers. So, quick history on the anatomy of a function. Now, there are a few layers in play when your function actually goes and gets executed, when it gets invoked. First, there's the compute substrate itself, which is my moniker for the compute infrastructure on which your serverless functions execute. And contrary to popular rumors, it is not made up of unicorns and pixie dust. There is some real stuff back there. But it's invisible to you. You don't care about it. You don't manage it. It's largely invisible to you. What you do end up seeing is what I would refer to as the Lambda container, the portion or a slice of the compute substrate which we shape, depending on your function definition, that gets instantiated during a scale event. And as part of that, you see the runtime getting instantiated as a process, and then your code or your function code being instantiated as part of that. Now, when I say your function in this particular example, it specifically means the code that is executing inside the handler of your function, not necessarily the artifact that you're uploading. Anything that's written outside your handler will be considered part of the overall environment, right? So basic stuff, just laying out the foundation of that. When an actual invoke comes into the function, it goes through a certain cycle. In the back end, the compute substrate downloads your code from our internal repository if it's never seen it before. It starts a new container, shaped, defined, with resources isolated for executing your specific function. It bootstraps the runtime for the first time if it is not loaded ever, and then actually goes and executes your code, initializes your libraries, dependencies, executes your code, etc. This is the part that many of you have heard of, which is the infamous cold start, right? The first time your function actually executes, there's a bunch of loading and initialization that happens, and the rest of it happens every single time your request executes. There's a part of this which AWS is responsible for optimizing, but when it comes to optimizing the entire cycle over here, it's a shared responsibility, right? Just to give you a sense, over the last year on the AWS half of the world, we have made changes, including some that are rolling out this month, which will reduce the overhead by almost 80% for some of the larger functions. But no matter what we do there, any of the optimizations, if they don't happen on the other end, you may not see the gains that you want. So the other thing I'll also call out is, while one box looks a lot bigger than the other, remember that your cold starts are happening 1% of your time. The application, or less, the application that you're actually working on is going to be predominantly looking at the warm start, and that's the one that's going to actually end up saving costs and reducing end-to-end latency. So we're going to look at both those pieces. This isn't just a theoretical diagram. You can actually see this using Amazon X-Ray as well. This is an example of what a rendering of an individual function actually looks like. You can see both the end-to-end latency, which is the box I drew up there, as well as the breakdown of cold starts, the function initialization time, and the overall time it takes to process, right? So you have visibility into what is going into each of those boxes when the invocation happens. You'll see that code shows up in two places over here, which means the first place you want to start optimizing is your code itself, right? And there are three different layers to think about here. First is your logic. Second, the dependencies that go with your function. Third is the archive or the dependency artifact that you actually end up giving into Lambda. My first call out is avoid fat or monolithic functions. And what this basically means is if you have multiple pieces of logic, if you find yourself writing a bunch of conditionals or routing logic inside your function, don't. More often than not, splitting it out into individual functions gives you the gain of cold starts on each one of those. And the actual difference in terms of manageability is a reasonable trade-off over there. Now, your mileage may vary. You may have a case where you're trying to call a function within a function within a function within a function. I don't know why you would do that, but in those kind of cases, please collapse the function into one, do what makes sense for your business. But in general, what we have seen is you will see better performance characteristics with separated functions rather than individual ones. Second, control your dependencies. What we are used to in a conventional development form is centralized dependency management, package the whole thing in, let the whole thing run, and then we sit and say, oh, my function is taking too long to load. Specifically, we see this a lot with Java, and I'll give you an example over there of code. But the secondary aspect of that, think about is how you actually compress the archive you end up uploading into Lambda. So with languages like Node and Java, you have options like Browserify and Minify for compacting the archive. Those of you using the serverless framework, yes, some of you, there's actually a plugin that's available called Serverless Optimize that will do this on your behalf. It'll shrink the archive by significant sizes. For those of you who are using Java or actually using build solutions for creating your archive, there are configurations you can do to pick individual dependencies. One of the most common culprits we see when it comes to Java-based functions is customers loading the entire AWS SDK as part of their jar file. Now, if you look at this particular Maven configuration, it's a popular build tool that you use for creating Java archives. What I've done is I've only specified the S3 SDK requirement and the DynamoDB SDK requirement instead of using the entire SDK itself, which is what conventionally you end up doing by default. This does put a little bit more questions about how you think about your logic before creating the dependencies, but can make a big difference. This change shrunk my archive from 49 MB to 13 MB, right? So when you're shaving off 2/3 of your dependency size, you're actually going to see that 66% improvement both on the first and the third half of the box over there, both your cold start and your warm start. So always look through your dependencies to make sure you're stripping out what you don't need. All right, so we talked about the code, the packaging, the archive. Now, when your function actually starts executing, there's a specific behavior that you can use to your advantage. Lambda doesn't do concurrency intra-process. It literally spins up a copy of your code for every single individual request that's actually coming in, which means you don't need to, on one hand, you don't need to do things like writing blocking execution code, thinking about multi-threading inside your functions. You can if you want to. I'll talk a little bit about that. But keep in mind that you're processing individual events on individual containers, right? Which means anything that is not on the critical path for executing for an individual request, you could theoretically move outside your function, move it into the header, and have that only happen during container initialization time, right? So this can go for fat clients that you can do lazy loading on, connection pools or management that you can move outside the handler function. What this does is it shifts it from that warm start run, initializing for every single request and paying the quote-unquote penalty for that every single request into the cold start or the container start window of it, right? So you're trading off the 99% for the 1%. Generally a better practice to get more out of it. And finally, well, not finally, I'm like number 4 on my number list. Okay, so I've seen this practice where people use Lambda for copying data back and forth. Not necessarily a bad thing to do, but if you're using Lambda for pure I/O, you're probably doing it wrong. The practice you should be looking for is my function doing anything to transform the data that's moving forward? If all you're doing is transport, there's probably a better way for you to do it, a more cost-effective way to do it. The whole point of Lambda is to never pay for idle, and if you're just waiting for I/O, you're probably paying for idle in some form or the other. Now, if you have to do it, now obviously if your business logic requires you to read some data, make sure you're only reading what you actually need. Most of the AWS data sources offer some kind of filtering or compacting capabilities in terms of the data that comes in. Aurora offers query filters, DynamoDB has query filters, and now S3 has intra-object filters with the new Amazon S3 Select feature. Since it's relatively new, I want to show you a specific example over here. So we have this reference architecture for running MapReduce using Lambda. It's available on GitHub. The code sample, architecture, everything is there. Those of you checking email on your laptops can open up another window and look at it. But a simple change, if you look at this particular example, we were pretty happy with it. It used to do, I think, about 770 million rows in about 200 seconds, 11.2 cents for executing the whole thing. Great price point. in this specific example, what it was doing was looking at network lock data and looking for specific IPs and doing an aggregation of IP ranges. So we took that specific highlighted change and replaced it with a corresponding S3 select object. What it does is it only looks at the IP from the entire row and then pulls it out there. It shaved off half the duration and processing on that and reduced the cost by over a fifth, because we were also able to reduce memory a little bit. I'll talk about that quickly. But you see this just by changing very small portions of your logic and making optimal use of the other services that you're reading from, you're shaving off time. And remember, with Lambda, time is money, right? So every single second that you're shaving off for millions of requests could manifest as, hundreds of dollars in your actual savings that you end up. So speaking of memory, that's the other dial outside of your code that you actually have available. You can trim your logic, you can trim your dependencies, you can trim your package, but you also need to make sure that you're tuning your compute logic or compute resources available to match the code that's actually executing over here. Today we announced that Lambda now allows up to 3 gigs of memory. Till recently, it used to be of 1.5 gigs. For those of you unaware, a quick reminder that Lambda offers a single dial for pushing up your resources. Increase in memory gives you corresponding increases in CPU. In fact, going to 3 gigs now actually gives you access to 2 cores of compute. That has interesting implications on how you write your code. I'll talk a little bit about that. But the key takeaway here to remember, though, is larger memory doesn't always mean more expensive executions. It actually may end up giving you faster performance for the same price point. So we ran a benchmark of using a function that calculates all prime numbers under 1 million, ran it 1,000 times, and these were the numbers we actually got. And what you'll see is the run at 128 MB and the run at 1 gig actually cost roughly the same. There's a difference in the sixth decimal, so to speak, but it ran 10 times faster, right? So if you are able to get 10 times faster performance for the same price point, it's worth doing that level of experimentation. It's totally fine to pick one and start with it, but figure out what the appropriate dial is. There are multiple tools available for you to do this. You can use monitoring tools like the ones from New Relic, which actually aggregate data from looking at both from CloudWatch and X-Ray and give you this amazing heat map of what the distribution of latency looks like for you. They actually have a great blog where they did a 50% increase in memory and saw a 95th percentile improve from 3 to 2.1 seconds. Simple trade-off. If you prefer a much more automated method, there's another tool available for you on GitHub called Lambda Power Tuning. This is, again, written by Alex Casalboni from Cloud Academy. What it does is it uses step functions to automatically switch the memory of your function, run it in parallel for multiple runs, aggregates the data out or the output data from CloudWatch of what the execution time and memory setting was and tells you what the appropriate setting is. So instead of you manually doing the runs multiple times, you can just use this tuning tool to pick what the individual setting is, making it a lot more easier, right? And we can choose to say, there are various automation tools for doing it, but this is an important performance optimization for you to do. And something that I would encourage you to make part of your automation and testing regime anyways. You may have changes based on payload, architecture, infrastructure, et cetera, right? So I know I bought 3 gigs up, so I thought it'll be worth getting into the multi-threading debate as Peter and I were getting in backstage. So it's a maybe, right? Till recently, we've always said, don't bother with multi-threading. If you have a CPU-bound function, your function only gets access to all the resources allocated to in the container, which at best was 1 core, which means even if you spin up multiple threads, no matter what the language is, it's going to be contending for the same resources. You're not going to see a speed up. There's obviously an exception if you're doing an IO-bound workload. You can do optimizations like running the IO on a separate thread, doing a download and calculation separately, and doing your core computation on one. With greater than 1.8 gigs, though, with the new 3 gig functionality, we do give you access to multiple cores. So if you have an application, such as if you're using Python multiprocessing.pipe, or if you're trying to do some kind of ML models that lend them well to threading, you can actually leverage that capability on Lambda today to see performance optimizations. We have seen some experiments where you see about 30 to 40% gains for some of the ML models over there. So another tip to keep in mind. I'll finish with one of my pet peeves, which is the same thing I called out before, which is don't bother with orchestration within your code. That's an unusual way for you to try and spend money on Lambda. Do it if necessary, but avoid it, right? You're literally ending up paying for idle, which is what we're trying to fight over there. The better property to do, if you have logic which requires to do this, is actually split it up into two functions. Do one that does the pre-processing, the one that does the post-processing, and then use step functions or some external orchestration mechanism to sequence between them. Now, recognize that you may not be able to use step functions for everything. There may be high traffic use cases where it's not possible. That's something that will obviously get better. But as a best practice, if you find yourself waiting for I/O, you probably want to switch to more of an external orchestration than doing that within your function. All right, so that's the end of the lean function kata. The main things to remember over here: concise logic, make it do only what it needs to do, read what it needs to do; efficient single function code, which means you're not ending up packaging things that you don't need, or libraries that you don't need, or logic you don't need, and take advantage of the ephemeral environment. All right? Cool. All right, so let's switch to the next layer over here, which is the actual invocation layer for stuff coming in, right? When we think about the execution of the Lambda function, because there's so much in a serverless architecture that depends on these various components talking to each other, how we choose the invocation mechanism makes a big difference, not only to the cost element of it, but also to the resiliency element of it. So, okay. So going back to the architecture diagram we talked about earlier, I'm specifically talking about the invocation parts that are highlighted. When you're using AWS services to actually invoke them, be it S3, be it Kinesis, one of the data stores available over there, AWS controls the invocation path and the optimizations in play. We build in retries, we try to compact the payload, we use efficient mechanisms from the wire so that it gets translated between the servers. But most of you have use cases where you control the payload. Now, this could be you're generating data from a machine or an IoT device and funneling it through Kinesis. You have customers who are generating payloads that are coming in through API gateway. In that case, you need to make some choices about how you actually end up routing and staging these invocations to your function, right? So first, make sure that you look at your application and choose an appropriate entry point. This is somewhat heresy on my part, but there are cases where you don't need to use API gateway, right? We have customers who have a single function working with a single client with no need for customization or ever having plans for exposing to anything else, right? In that case, API gateway is great for future resiliency and kind of doing an architectural split out over there, but you may actually see faster response times and easier management layer by just using the AWS SDK to call it. Remember, Lambda exposes a direct invoke API, which is an HTTP endpoint, and you can send a signed request to it and get a response back from it immediately. Now, for the other 99% cases where you're actually using API gateway, you may also have the scenario where you're using machines to actually invoke your API, right? It's not just an end-user facing API coming from a mobile backend or a web backend, it's a machine-generated API. The way API gateway is structured underneath the covers, it actually uses CloudFront to have basically what we call edge-optimized requests. So everything is cached by default, routed through CloudFront so that you get a faster response if it's going outside the network. This can work against you if you have the thing coming from inside the AWS network. So for example, you have a process running on an EC2 instance that's calling this particular API. In this model, we recommend you actually use the regional endpoints capability of API Gateway. What it does is it takes CloudFront out of the equation, basically allows you to bring your own CloudFront. In our experiments, we have seen the overhead change from about 110 milliseconds to about 8 milliseconds. So hundreds of milliseconds in your entire response path can be shaved off by making that very, very simple switch, right? So apart from the synchronous pattern, when you think about things like S3 or even actually SNS, what's interesting over there is thinking about how many events are you processing. Rather than thinking about the end-to-end latency, it's the width of requests that are actually getting sent over to Lambda. A general pattern we see when customers are building, say, an image processing pipeline or routing events through SNS is they sign up Lambda to process all the invocations or requests that are coming in and having the first step of your function being the one that actually discards your function, right? This goes back to my point in the previous section, which is if you have routing or orchestration in your function, there's something off over there, right? Most services, at least within AWS, offer a way for you to discard events before they even get to Lambda. Way more cost effective. S3 has the capability of doing prefix and suffix filters, right, which allows you to lock down Lambda functions to trigger only on updates to certain paths inside your S3 bucket. SNS recently launched a capability for you to do message property-based filtering. So, for example, in your SNS payload, if you had a property that said, this is coming from originator A, and the other one is junk, you can literally say only process if it is junk or originator A or whatever you so choose. This has direct proportional impact on your costs. Lambda has request and execution-based pricing, which means if you trim a third of the events going to your function, you're saving a third of your cost, right? Just straight up. No change to your processing, you're just eliminating it earlier up. So as a best practice, look at the configuration on what is actually going and invoking over there. If you continue to use a custom event and you control it, there's a bare minimum that should be in the event itself, right, which is what we call provenance, so to speak. You should be able to say where the event came from, who the identifier is, what timestamp was involved over there. Everything else in more common patterns is optional. In fact, I would encourage you to lean towards as slim invocation packages as possible. Avoid large responses and large requests going into your function. You're going to end up adding more bandwidth. You're going to end up adding, if you're doing cross-region calls, you're going to actually see network costs associated with the invocation. Instead, use a staging semantic like S3 or others to capture the payload and then invoke your function. So, for example, if you're trying to do image processing inside your function and you have API gateway fronting your function, have a route through your gateway that ends up putting the image into S3 first or a direct connect into there, and then have Lambda go and read from that object rather than trying to funnel the whole thing to Lambda through the entire payload as it goes. There are various constraints that both API gateway and Lambda apply as well. For asynchronous invocations, there's only up to 128K that's available, so keep those kind of constraints in mind. One really interesting element over here is, especially for API gateway, you can control the protocol that gets passed on into Lambda, right? JSON's great, it's very machine readable, but sometimes there are other protocols out there that you can use for tuning the responses back. So this is an example of swapping out the JSON response coming into Lambda and processing it for protobuf, or protocol buffers. This uses the API gateway capability of supporting binary requests and responses. You can set the response type to binary, change the header to protobufs, and you can actually just pass any service that can emit protocol buffers out there. The code here is slightly different. You see that there are, I guess this doesn't have there are extra layers over here for reading the protobuf library, transforming it back into something that your function can actually execute, and then responding with a specific protobuf header so that you're responding or your client actually knows what it's reading back. But if you get up to like a 40% smaller response in this particular example, that again can end up looking a much more leaner and faster responsive function for you, right? So look at all three layers: what's invoking your function, what it's actually passing into your application, and what mechanism it is using to pass of those. Each of those has opportunities for you to trim things back over there. So most of these accrue towards sort of a cost reduction element of invocations. What about resilience, right? And here, there's this construct which I like to call an event store, which should or should not play a part in your architecture depending on your choice, right? So what do I mean by this? For many applications, we look at saying Lambda comes in or a request comes in through a router like IoT or API gateway, turns around and invokes your Lambda function, which is great. But you may have cases where you say these events need to be stable even if the one emitting it goes down, or these needs to be persisted in some durable fashion if Lambda goes down, or it needs to be retried if for some reason Lambda fails. Kinesis tends to be a favorite one for many data processing applications. You use Kinesis as the bridge between your ingress point and Lambda. You use Kinesis as your streaming mechanism for turning around and processing those applications. SQS is another viable choice, and there are different models for both of these, right? If you use a streaming-based event source, you get things like ordering guarantees, you get things like concurrency guarantees, but you're restricted in terms of the fan-out that you can actually do. Something like a queue gives you the opposite semantics. You can actually do retry behaviors, you can get much more concurrency, but you lose things like ordering semantics and some kind of retrieval mechanism on it. Both of these are built in to some of the AWS services that you use. So for example, DynamoDB Streams is an event store for DynamoDB Stream, for DynamoDB updates, right? It gives you a persistent mechanism for seeing what the change log look like. Lambda's async API has a queue built in, so it gives you an event store baked into it so that we can do retry policies underneath the covers. But if you are constructing your own serverless / event-driven architecture, this becomes an important architectural consideration for you to put in. There's obviously a cost versus durability trade-off here. You're bringing in another service, you're bringing in another component that you now have to manage, but it can have a pretty significant impact on the durability of your function because you now have events actually being captured and available for replay. Right? Oops. Sorry. I seem to have lost a slide somewhere. All right, I guess I'll just have to go backwards. So, sorry about that. Okay, so quick reminder, Lambda thinks of its scale in terms of concurrency. It's not request-based, it's not duration-based, right? Concurrency is a unit of essentially your request rate into your duration of your function, and the processing model is slightly different depending on how you invoke your Lambda. If you're calling it straightforward directly through the API, or you're using a synchronous mechanism, Lambda will spin up as many copies as required for each individual request. If you're using a queue-based or an async mechanism for doing so, be it your own queue store, you still get the concurrency behavior over there, except the events themselves are retained for some window of time, making it available for retries. And then if it's stream-based, it's slightly different because now your concurrency is driven by the ordering on the stream source itself. So if you're using something like Kinesis, your concurrency is driven by the number of shards that are on that Kinesis stream, so that you basically can maintain the ordering guarantee of processing on each one of those. Now, this has interesting implications on both your end-to-end processing as well as your resiliency. So I'm sorry about the thing, but I'm going to skip back. Okay, so when it comes to streams, your concurrency has, your latency has an interesting impact on your concurrency, right? Your maximum theoretical throughput when you're using a stream-based processing application is the number of shards which drives the concurrency of your function into about 2 megs per second, which is the output that you get from Kinesis. What this means is if your number of shards, if your function is taking longer to process because the effective theoretical throughput is driven by that, if your function is taking longer to process, your concurrency becomes a bottleneck. It'll cause your data to start backing up over there, right? Because your throughput is not getting gated over there. So the only way for you to make your end-to-end latency faster and keep it going is to increase the concurrency. Obviously, you can make your function run faster, but if it is what it is, if you're seeing your end-to-end latency slow down, increasing concurrency or the number of shards on your Kinesis stream may be the way for you to see optimization. If you're using a queue-based mechanism, though, it's the inverse, right? Your concurrency is only bound by the overall account limit that you have, 40,000 or 100,000 or as much as you guys have right now, but your duration has a direct impact on how much concurrency you can avail, right? So the pattern we see is someone had a function running at 20,000 TPS, and suddenly they start seeing throttling at 5,000 TPS. And when they go and look at their numbers, they find that their duration jumped up to 10 seconds because it was getting throttled by some downstream service or some kind of timeouts were happening. So a direct impact on the latency can cause your concurrency to actually flatten out just because, cause your request rate to flatten out because your concurrency stays the same, but your duration actually went up. So the practice for you to remember, depending on how you're architected, is to make sure that you're looking at the new concurrency metric. So if you go to your console right now, you will see a new metric in there that says concurrent invocations that tells you what is the effective concurrency that is available for your account level as well as your individual functions. This becomes another important one to monitor and track, and Peter will be talking a little bit more about this once we get there. All right. I'm all about the slides today. Okay, so the last one I leave you with is how you end up architecting has impact on the internal retry policies as well. If you're using services that we have, like Kinesis and SNS, or even Lambda's async API itself, there are some retries built in, right? If you do async, you have up to 2 retries. If you're using Kinesis, it actually has essentially an infinite retry till the data replay happens. A tool that many people overlook here for resiliency, though, is using a dead letter queue, right? When you have an event-driven system where events are flowing through it, Lambda supports the concept of a dead letter queue, either using SQS or SNS, that captures the failed events that did not get processed and then make it available for retry, right? So you can essentially build as many or as complex a retry procedure that you care about outside of the retry modules that Lambda itself provides, okay? So this goes back into that resiliency construct. Like you have to think through what are the failure paths that happen inside your Lambda function and set these controls in place. But more often than not, DLQ makes it much more resilient for you to go forward. Now, this is not something that's available for Kinesis. Some people tell us that they want to dial down the retry policy that we have for Kinesis because it's very aggressive. But there's actually a way for you to simulate this behavior quite easily with any of the services, really. And that's by using SNS. So SNS, Simple Notification Service, actually has its own DLQ built in. Same mechanism as Lambda. You can route it to an SQS queue. In this particular example, the failed events from Kinesis being processed, instead of sending back an error to Kinesis, which triggers the retry behavior, it says my execution actually succeeded and dumps the payload out into SNS and does a retry through that particular mechanism. Now, the caveat I would put here is this only works if for some reason in your Kinesis stream you do not care about the ordering guarantee that's in place, but at least gives you a way to capture the payload that's coming out and then go moving forward over there, right? Okay, so on that invocation front, kind of coming back to it, it's about succinct payloads, making sure that what you're passing into your function is very specific, making sure that the routing layer or the service that you're picking to get your events to your functions has constructs of resiliency built into it, either in the mode that it's invoking it or the way it's routing it. And then finally, remember, design your application for concurrent executions, right? It's not about request rates, not about duration. Watch your concurrency. That's what's going to make or break how your application is functioning over there. All right, last part, and then you get to hear Peter more than I do. All right, so last part, Lambda talking to downstream services, the Kata 3, is thinking about coordinated calls, right? And this becomes important because Lambda is somewhat unique in its behavior. The sort of behavior of automatically spinning up and down, automatically running idempotent copies of your function, all of those become somewhat unique when it comes to compute layers, right? One call out is, and this is again more of a best practice than a must do, is making sure that the way you're setting up your application has APIs as contracts. The reason this becomes important, especially in a Lambda world, is because separation of concerns, especially when you're talking about scale guarantees, having something like an API in between allows you to separate those out. So in this example, suppose this is a theoretical ingestion service that gets processed by a metadata extraction service that's fronted by a front-end service, right, with 3 separate APIs over here. If for some reason there's a data surge in my ingestion service, you can actually use the API on the metadata service as a way to rate limit it or throttle it down, because there is a separation of concern over there. And that prevents you from DOSing the actual database which is sitting behind the Lambda service, right, which is the one that you're talking over here. So again, this may not be always possible. This may not be always possible out of the door. This may be something that you're already doing for other microservices-based approaches, but it becomes especially important when you're building serverless architectures because the contract is your border of resiliency as well between these particular services. When it comes to non-API calls that you're making, say databases or others, you need to have what I call scale matching, right? Most databases, especially when you talk about relational databases, have unique behaviors when you talk about scaling it in and out. There are a finite number of connections it can handle. There may be APIs that can only handle finite number of calls. You may be having this old crufty thing sitting on-prem that you need to call out to. All of those have certain limitations that you can't go to. Make sure that when Lambda is calling out to them, you're matching your scale configuration for Lambda to it. Now, this is a control we actually just rolled out today. You can actually specify the concurrency or the max concurrency for individual functions, right? What this allows you to do is, you remember that concurrency diagram we were talking about, restrict an individual function from fanning out beyond a certain limit. It also acts as a reservation. So if you have one function going AWOL on one end, you can come back and say, no, lock it out or lock it forward. But this gives you a way for building guarantees or isolation around individual functions, especially when it's interacting with multiple other services. Okay? The diagram at the bottom actually shows you the new concurrency mechanism in Access. I gave my individual function an amazing limit of just 5 concurrent executions, and you'll see that in the green line in the diagram, it actually gets capped at that particular limit, stays that way, and then goes back down, right? So this kind of behavior allows you to match, for example, the max number of connections that your database can handle, the max number of ENIs or IPs that you may have in a VPC subnet that you configure to your function, essentially having a little bit more control on the scale behavior over there, right? Again, because of the resiliency factor, a database outage is an outage for your function, right? It's an outage for your application. You want to protect the data. You want to make sure that because Lambda has retry behaviors at that particular layer, if you've done the event configuration correctly before, you want to prevent Lambda from taking down anything else over there rather than having any other configurations in place. And last one I'll call out on the security front is about the VPC configuration, right? Many of us think about VPC as an amazing security and isolation mechanism in place. And the compute substrate that I referred to earlier on, by default, runs your functions within a VPC. There's no way for any external actor to access those functions in our compute environment. It's only through the invocation or the APIs that Lambda itself provides. So when you ask yourself the question of should your Lambda be in a VPC, the only situation where you need to think about having access to your, giving VPC configurations to your Lambda function is if it needs to access a resource that's within a VPC, right? Database, Elasticache, private APIs, what have you. For anything else, don't bother configuring a VPC for your function because it has implications on both your latency and resiliency. If you do have it, make sure that you put Lambda in a subnet with NAT access because you have services such as CloudWatch, you have services such as Kinesis or S3 that will be part of your application logic that you actually may need to go and have access to, and that requires you to go through internet access. If for some reason your service only requires resources within it, then put it in a private subnet only, right? Don't bother with it. This diagram is probably with better colors rendered in our documentation as well, so it's available for you for reference. So what trade-off does it have on your latency and your resiliency? Remember the cold start diagram we talked about earlier. You'll see there are now two more blocks that show up, which is using the setup of network interfaces and instantiating or attaching those network interfaces to the portion of the compute substrate where your Lambda function is executing. These are not fast operations. It just takes time, right? These could take up to multiple seconds to instantiate, and we have done a bunch of work to try and minimize the impact of that on your invocation. But the reality of it is, it will add invocation time or to your cold starts over there, as small as the add it may be. So if you are choosing to do so, be cognizant of that particular impact that it's going to do it, right? So in the worst case scenario, if you have an application that has an RDS instance, that has VPC, where you have taken a fully stocked AWS SDK, stuffed it into a jar file, and put it in front of an API, and then you're looking for a 100-millisecond response, you're not going to get it, right? It's just not. Your P99 is not going to be that. There'll be other parts which will be. So be aware of that particular decision before you go forth and put it over there. The other element which has a trade-off on is resilience. Giving Lambda functions access to your VPC is very powerful because you control the network substrate, you can get private isolation, everything is great, but it also means you now control it, which means you also now have a shared responsibility in the availability of that particular function. We require you to make sure that the VPC is available across multiple availability zones, something that we do by default when we're executing the function. The isolation behavior I would recommend is making sure you give Lambda its own dedicated subnets so that you don't accidentally, as Lambda scales up or down, doesn't accidentally end up draining the subnets for someone else who needs it. And finally, the same reminder I gave you before is that if your function needs to talk to the internet, make sure that it's set up with a NAT, right? So this was relatively more compact because once Lambdas execute, a lot of the optimizations we talked about earlier about fixing your function and invoking it get you a long way in what your logic executes as well. But for your downstream calls, keep these three things in mind. Try to decouple as much as possible through APIs so that you have clean separation and isolation. Make sure that you're scale matching to your resources that have scale constraints and that you're securing them appropriately using the appropriate isolation mechanisms as needed. All right, so with that, we've kind of covered a lot of the theoretical possibilities over here. I wanted to invite Peter Spassky on stage to tell you how they actually put a lot of these pieces into practice at A Cloud Guru. Peter?
Thanks, AJ. Hello, how's everybody doing? Good, excellent. Is anybody excited for replay? Yes, I am very excited. Yeah, absolutely. So look, I'm very pleased to join you today and to join AJ on this stage. And I will talk about serviceful operations. I guess the one takeaway that I have for all of you is that in the end, everything depends on people. Everything is up to you. So you can be given access to the best technology like Lambda, to best opportunities, but you need to enable your people to succeed. And that includes education and guidance. It includes setting the right process. And it includes instilling that culture of automation and innovation. Next slide. So I work for a company called A Cloud Guru. And our mission is to teach cloud computing to the world. So we have online courses that allow you to learn AWS. We have courses that cover serverless, help you study for an AWS certification, or get kind of in-depth insight into topics like security. So we started 2 years ago, and we built an entirely serverless company. In fact, we were doing serverless before anybody even said the word serverless. I think we were using Lambda, and you couldn't even call it from the web, right? There was no API gateway. And we are an interesting case study because we are a startup, yet we have 400,000 people. And we've been able to do it all serverlessly. So we have a rich web application, mobile apps, and you don't need a server to do any of that. So that's great. So let's take a look at some weekly stats and what we do. So on average, a week, we execute 6.21 million Lambda invocations. That's quite a good amount. We have 480 Lambda functions across 15 environments, and this includes test environments as well. And we do approximately 4 million API requests using API Gateway. There's the production BFF service that does 3.97 million requests. In this case, BFF stands for backend for frontends, not best friends forever, just letting you know. And that's our GraphQL endpoint. And I think I'm actually excited about AppSync, the new GraphQL managed service that AWS has released. I'm sure our team will evaluate that as well. We have 142 buckets with over 2 terabytes of data. And we serve almost 7 terabytes of data weekly using CloudFront. So why am I telling you this? This is because all the tips that AJ just shared with you are extremely important to us because we need to optimize the performance of our application. Let's say if, on average, our functions take 101 milliseconds to execute. If we shave off 2 milliseconds and go to 99 milliseconds average execution time, we have effectively halved our bill. And at our scale, that means something. So the 3 things that I kind of want to talk to you about today are automation, monitoring, and innovation. So let's start with automation first. So serverless applications, as you know, are distributed by nature, right? There's no way you can get away from it. And so we have numerous Lambda functions. We have our single-page application. We have various services that we need to deploy to and update. We need to make changes to Firebase, which is our real-time streaming database. And it's impossible to do it well without automation and testing. So you can see in the diagram that we have GitHub, right? We use GitHub, which connects to Travis CI. Travis CI then deploys to AWS. It can deploy or update other services, and it can also deploy our front end. And that's quite a normal setup that you would have seen, I don't know, many times before. We also use serverless framework, kind of for orchestration and deployment. And we use Ansible for our dev environment. So we kind of deploy some additional CloudFormation scripts. So just a few tips that we learned is that, obviously don't go serverless without automating the provision and deployment of your application first. In fact, I would recommend set up your deployment pipeline and only then begin working on your application. Obviously, mandate the use of frameworks such as SAM or serverless framework. It's a must. Have a look at other frameworks as well, like Chalice or Apex. And instill the culture of automation. Furthermore, there is no such thing as NoOps. That doesn't exist, right? So DevOps is important. So make sure you know how to contact AWS support. Make friends with them. Think about how you are going to do DevOps when going serverless. When it comes to testing, again, extremely important, because for us, our code is our infrastructure. It is our application. So we need to have a thorough test coverage. And we use Selenium, we use Jester, and Travis CI executes all those tests for us. Obviously, we don't merge or we don't deploy if there are any problems or any tests fail. And if you've been doing that kind of manual user-driven testing, it's not going to work for you in a serverless scenario, right? Because you can't really emulate AWS locally. You would have to then kind of deploy to AWS, test things, redeploy, fix. It's a terrible process. So you have to have a thorough test coverage. And we test our components at a different level of granularity, right? Our test process even hits the API gateway in the process. The other important aspect that we've tried to instill in our company is that of monitoring, right? So you need to be aware of what's going on inside your system, right? How do you know if a component is failing? I mean, it's a distributed system. It could be hard to detect what's going on. So use alerts, but make sure kind of to calibrate the signal-to-noise ratio. Explore third-party tooling. You don't have to use just AWS services. Sorry, AJ. So we've explored things like Sumo Logic, and there's other tooling that you can have a look at. Use services like X-Ray to get a holistic understanding of your system. Distributed systems are hard. We have CloudTrail enabled for everything, and so should you. So we have something like 566 alarms, which is about 4 alarms per production Lambda. And so we have an alarm that will notify us if there's more than one error every 5 minutes, if the duration of the function kind of was longer than we expected, if the function ran many more times than we expect, or if functions were throttled. Here's another service we use called RunScope. And what it does, it helps us to monitor the responsiveness and latency of our system, right? So it continuously makes requests to CloudFront to detect whether we can access our files. It hits Auth0, which is our authentication solution. It hits Firebase. It hits our API. It hits our front end. And look, we'd rather find out from RunScope that something bad is going on than from our users. And it's a great thing because let's say our GraphQL API starts having issues, latency spikes up or it goes down. We can immediately detect it, and we can start doing something about it, right? We can see, okay, is it something that we deployed recently that's causing an issue? Or is it an outage in some other part of the system? We can notify our users. We can begin an active investigation, put workarounds. So you have to be acutely aware of what's going on, and you will do it with monitoring. Another important thing to remember is, obviously security, and it's actually quite easy to forget in serverless context. I think some of us have that, kind of thinking that our cloud provider, AWS, will take care of everything. It's actually joint responsibility, right? AWS takes care of some stuff, but we have to take care of a few things as well. So make sure that your IAM roles, users, and policies are as tight as they can be, right? Have a role per function. Explore third-party tooling as well to help you figure out if your permissions are too loose. Use things like AWS KMS whenever possible. And make sure to understand that as you add more services and endpoints, your surface area for attack increases. Which brings me to OWASP Top 10. And Mark Nanakoven did an excellent presentation about it at ServerlessConf New York a few months ago. And I'm sure a lot of you will be familiar with this. These are kind of the top 10 threats. And it's interesting how they apply to kind of our serverless environment now. Let's take injection. When we talk about injection, we usually think of SQL injection, right? But what about Lambda? Could you actually inject some code into Lambda, some bad code or something, and have our Lambda function executed? Maybe it's possible. And in fact, I have a feeling that over the years, as kind of serverless eats the world, we'll see those attacks happen. Yeah. Security misconfiguration, easy to do those. Using components with known vulnerabilities, very easy. Like we use Node.js, right, for our functions. And usually you install, a dependency and it downloads half the entire internet alongside with it, right? So you have half the entire internet, you package up your Lambda function, deploy it, but then how do you know if one of those dependencies is out of date? Do you have a process in place? So we do. We look at all the new patches that come out and all the new updates, and so should you. And finally, this one, insufficient logging and monitoring. And I reckon it's a problem in our serverless community because I get a lot of people asking me about this. How do you do your monitoring and logging? So I kind of just spoke about how we do it, but I urge you to think about it. And finally, let's talk about innovation. And this is, I guess, it's a bit of a fuzzy topic, but I've come to a few realizations that I want to share with you. Look, ultimately, the tips and the tricks and the processes and the patterns that AJ shared today with you will be applied incrementally as you progress through your journey, right? They won't happen overnight. So, and this applies to your architecture too. You can start with one type of architecture and then transition it to another type of architecture. And this happened with us at Cloud Guru. We started and we basically built a serverless monolith. We had one database, we had a bunch of functions that all spoke to that database. And we scaled to about 200,000 users. But then we realized that we needed to scale even further, and we needed to go to a microservices approach because we wanted to scale our components individually as well. And we wanted to have teams work on components kind of individually, not step on each other's toes. So we were able to transition from a serverless monolith to microservices just by changing some of our code and changing the serverless.yaml file. It's quite incredible that we didn't need to provision any new environments. We didn't need to provision any new service, anything like that. It was just all done in code. So that's the magic of serverlessness, right? We were able to kind of evolve a lot quicker than normally you or I could. So look, make the trade-offs that are relevant to your business, right? Maybe you may have to go hybrid and do serverless and containers, but don't be scared. You will be able to evolve your architecture. So AJ said to me that it's not anarchy, it's agility, and I love that. And just a few more slides. As you evolve, best practice will change. This is still early days yet, so please learn from the community and contribute back to the community as well. When we started, SAM didn't exist, serverless framework didn't exist, so we rolled our own deployment scripts using Grunt, and that worked very well. Then we were able to migrate to serverless framework, which was created by the community, and that was great as well. And this leads me to kind of my final point here, that, look, there is a human hack here as well. Going serverless is fun, right? It's inspirational. If you announce a project that's serverless at your workplace, you are likely to get very passionate developers joining that project, right? Because they love this kind of thing. So they will put in a lot of effort and a lot of energy and love into what they do. So apart from all the technical niceties that we get from it, there's also, I think, that human element that you get from it as well. And look, our team was very passionate. These are some of the public projects that they've created, like serverless Docker before SAM Local came out. So yeah, and some other projects as well, like the serverless plugin for pushing CloudWatch data to Sumo Logic. So you get passionate people. So my final message is this, right? Serverless is about people, and it's about a mindset change. It's about a mindset change towards automation, towards agility, towards automation. As someone said, developers, 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 developers. Thank you so much.
Yes, thank you.
Thank you.
Thank you, Peter. We expect you to continue to lead the community charge for us, so thank you. So with that, just to kind of recap quickly there, right? The whole idea is everything that you see as best practices needs to be embodied as automation inside your operations. All those best practices or deviances from them can be detected through monitoring. And ultimately, the model for adopting them is going to be driven by sort of this agility or innovation mindset. You have to be okay taking these one at a time. You're not going to get it right on the first shot, but it's okay. It allows you to move pretty quickly in a much more safe fashion. All right, so what did we talk about today? So we said, wow, that did not animate the way I wanted it to. But anyway, here it is. So we talked about the lean function, concise code, concise logic, efficient code. Think about your ephemeral environment. We talked about the eventful invocations kata, succinct payloads, resilient gateways, and concurrent executions to keep in mind. Make sure that your calls to your downstream services are decoupled in some form or fashion. Scale match to make sure they're accommodating the downstream services themselves and secured appropriately. And finally, make sure that your operations are set up in a way to absorb all these practices together. So congratulations, all of you. You now have a black belt in serverless applications. All right. So there are a lot of topics we mentioned but didn't dive into. There are a lot more existing talks about monitoring and operations in a serverless world, migrations, working with databases, et cetera. Highly encouraged to dive deeper into it. They go much deeper into some of the topics we touched upon over here in Periphery. Thank you so much, and we'll hang out more for questions downstream. Thank you.